Hi, we're going to continue on with section 3.1. This time we're going to talk about mixtures. Last time we talked about pure substances, elements and compounds. So today this is a different type of substance. This is a mixture. You're also going to hear my dog snoring in the background. That was her. Okay. So a mixture, as opposed to a pure substance, has two or more different substances that are just physically mixed. They are not necessarily in the same proportion every time. What that means is you don't always have the same amounts of each substance. So think of, let's say, a chocolate chip cookie. You don't always get the same number of chocolate chips in each cookie. That's a different proportion of chocolate chip to cookie batter, whatever you want to call it. These mixtures can be broken down by physical means. What do we look for? We look for two substances in the same container, and then ask yourself, can the amount of each substance change? If the answer to that is yes, then that means it's a mixture. Okay, so let's go over some of these terms. What does physically mixed mean? Physically mixed means that they're just in the same container together. So there she goes. That's a snoring dog. Just in the same container. All right. So, for example, if we have something like calcium, which is a solid, and then we put that in a container with magnesium. Those are both solids. Now notice it's element and element. Okay? That lets you know that it's a mixture. But they're physically mixed. In other words, they are not chemically bonded. So they just happen to be in the same container together. So there's one atom. Here's another type of atom. All right. What does same proportion mean? So when we say that it does not have to be in the same proportion, that means that the ratio between the components can change. So the example that I gave you was a chocolate chip cookie has a different number of chocolate chips per every cookie or per batter. Some other examples that I can give you, let's say sand in water, right? So sand is silicon dioxide, water is H2O. If I have a bucket and I put sand in there and then I put some water in there as well, does the sand to water ratio always have to be the same? If the answer is no, the ratio does not always have to be the same, then we're talking about a mixture. Now, let's compare that to something that does always have the same ratio. We mentioned it earlier, sodium chloride, NaCl. This is a compound. This is not a mixture. And the reason why we know it's not a mixture is every time we get that sodium chloride, it's always the same. Every time you buy just table salt, it's always the same. The ratio is 1 Na for every 1 Cl. We can't say that about the sand and water. It's not always the same ratio of sand to water. Now, these can be separated by physical means. What does that mean? That means that we can actually think about that sand and water. I can separate that sand from water by filtering it out. So I can set up a filter. Here's a piece of filter paper. And if I pour this container into my funnel, then the sand will be stuck in the filter and the water will come out. That's physical means. That's not a chemical reaction. Now, when we're talking about mixtures, mixtures can either be homogeneous or heterogeneous. A homogeneous mixture is always the same throughout. It has the uniform composition. It's always the same. no matter where I get it from. Okay, so a good example of that is salt water. So long as all the salt is dissolved, if I take salt water from the top and if I take salt water from the bottom, it should be the same. So that's going to be a homogeneous mixture. Okay, and again, that example was sodium chloride, salt, and water. When I look at that, it should look the same all the way throughout. There's no difference. If I want to look at particles, so a homogeneous mixture in the particle view will look something like this. And I'm not necessarily drawing sodium chloride and water. I'm just drawing what a homogeneous mixture is going to look like here for you. Okay, so you can see that I have very similar sample throughout. Okay, but it's in a container, they're not bonded to each other, it's just a mixture. That's homogeneous. Heterogeneous has different layers. So a good example of a heterogeneous mixture would be oil and water. So you've all seen oil and water, I'm sure. When we mix oil and water, the oil rises to the top and the water is on bottom. Now that's a mixture because they are not chemically combined, they just happen to be in the same container. Again, another question we can answer is, will oil and water always have the same ratio? Will I always have the same amount of oil to water? The answer is no, then it's a mixture. But if I take a sample from up here, as opposed to a sample from down there, I'm going to get two different samples. And that's how we know it's a heterogeneous mixture. Now, we can compare all of this information here by just looking at this one little graphic. Okay? So matter is an umbrella category. Anything that you can touch is matter. All right? Matter can be broken up into pure substances, and then pure substances are either elements or compounds. And the reason why it's a pure substance is because it's always found in the same ratio. No matter where you find that pure substance, it's always the same. Now, if it's not a pure substance, then it has to be a mixture. A mixture can be a homogeneous mixture or a heterogeneous mixture. Here's an example of a homogeneous mixture, brass. Brass is copper and zinc. Notice the word and. Or, in this case, for some reason, we have pennies inside a glass of water. So, again, notice the word and. That lets you know that it's a mixture, but I've got different layers. I've got this copper layer, and then I've got this water layer. Okay? So there's a mixture, and there's tying it back in to a pure substance.